You got minus, what was it, 810.44? All right, now let me ask you this. At higher temperature, did the driving force go up or did the driving force go down? It changed because before it was what, minus 8? What was it before? Minus 8, yeah. Actually, I lost my calculation. You'll have to tell me. Before it was minus 818 at 298. Now it's minus 810.44 at 330 Kelvin. So we raised the temperature. Did the driving force go up or did the driving force go down? So delta G, did delta G decrease or did delta G increase? It's confusing with these negative numbers, isn't it? But you know about energies. Minus $10, minus $20. Which one's bigger? Some people will say minus $10 because that's more positive, closer to zero, right? Some people will say minus $20 is bigger. What do you say? Just bigger. Which one's bigger? Minus $20 or minus $10? Both of them?
Yeah.
I'm going to trade you my minus $10 for minus $20. Or would that be a sensible trade?
10 is bigger in that sense.
This is different than minus 10 degrees versus minus 20 degrees. Which one is bigger? Temperature. Minus 10.
Is on a scale.
Minus 10 degrees is warmer than minus 20 degrees, right? It's a higher temperature. For energy, though, and for money, which one's bigger? Minus 20 or minus 10? Minus 20, yeah. Minus 20. And so what happened was the driving force went down. Actually, it didn't go up. The driving force went down. And the driving force decreased because the driving force, according to the second law of thermodynamics, is delta S of the universe should increase. That's going to lead to a bigger driving force. And so we want delta S of the universe to be more positive. And that means delta G should be more negative here. And so this is a bigger driving force because it's more negative than this. Does that make sense? In other words, this is a bigger amount of energy than this. It's just negative. So a higher temperature. But the tricky thing is this is thermodynamics. There's one other factor that we have to consider, and that's kinetics. When you heat things up, they tend to react faster. They might not have as big of a driving force, but they'll have a faster reaction. So to really understand chemical reactions, we need to understand both the thermodynamics, what we're doing here, driving force, and the kinetics, the speed of the reaction, to fully understand things. We're ignoring the kinetics right now. We're just looking at the thermodynamics of this. And so basically the driving force went down. So the higher the temperature, wow, the lower the driving force. That's kind of counterintuitive because normally when we increase the temperature, we tend to see it increase in speed, which we take as an increase in driving force. And oftentimes that is the case, but sometimes it isn't. Now, that means this reaction has a bigger driving force at not higher temperature. This reaction has a bigger driving force at a lower temperature. But at lower temperature, it kind of reacts slowly, even though it's going to yield more free energy that you can do work with at lower temperature. Is it possible to keep decreasing the driving force such that there's no more driving force? Is that possible? We decrease the driving force. Can I keep decreasing it eventually to 0? You know, I increase the temperature and that decreases the driving force. So can I just keep increasing and increasing and increasing the temperature until it goes to 0? Let's take a look. So right now, delta G is negative. Delta G is negative. It means forward reactions favored. Forward direction spontaneous. This is negative. This is spontaneous. This happens to be more spontaneous than this. This is more negative. Here, we're going to be at equilibrium. Here, we're actually going to shift it so that the reverse reaction is favored. That is, CO2 plus water is favored. That doesn't mean it's going to happen because mechanistically it's kind of hard to do that, but let's take a look.
Kinetics take over. This won't work.
It would be hard to reverse because, yeah, kinetics and side reactions would probably take over and you'll form stuff that you weren't intending to form. And so if we were to analyze this, delta G at temperature T under standard conditions is equal to delta H at temperature T under standard conditions minus T delta S under standard conditions at temperature T. And then we made an assumption, since appendix D is kind of limited and we're stuck with 298 Kelvin, we're going to make the assumption that delta H doesn't change much. So we're going to use the 298 Kelvin value for this minus T delta S at 298 Kelvin. And then we plugged in the numbers here. The delta H is very favorable. That was minus 890.66, was it? 0.63. This is favorable because what's happening here is energy is going down. You know, it's exothermic. And so we're minimizing energy. Minus T. And then we look at delta S. Delta S is minus, I'm going to convert it to kilojoules, minus 24298 kilojoules per Kelvin. This is unfavorable. It's unfavorable because we're increasing entropy. And so increasing entropy means we're not increasing. Increasing is favorable. Sorry, we're decreasing entropy. It's negative. we want to maximize entropy, but that's not happening here. What's happening in this case is the entropy is actually going down, which means it's getting or becoming more ordered. Does this make sense? The entropy is going down in this. And so we're minimizing entropy. Is it becoming more ordered by about 200 joules? Well, that seems about right, because let's take a look. Oh, it's gone. We'll take a look at the reaction again here. It's CH4 plus 2 O2s. And all 3 moles here are gases. I have 1 mole of methane, 2 moles of oxygen, 3 moles of gas. This is going to CO2, gas, which is 1 mole of gas, plus 2 moles of liquid, 2 moles of H2O liquid. And so it's becoming more ordered. We're going from 3 moles of gas to 1 mole of gas plus 2 moles of liquid. Do you see that the entropy is actually going down? The gases are more disordered, less constrained. Liquids are more ordered, more constrained. And so this is unfavorable here. But do you see there's an adjustable variable here, and that's the temperature. If I increase the temperature, will it make it more favorable or less favorable? So if I increase the temperature, I'm increasing the entropy term. By increasing the entropy term, I'm making it less favorable, more unfavorable. If I decrease the temperature, then I'm minimizing this unfavorable term here. And so what I'm going to do is I'm going to just try to increase it a lot. And so overall, what I want to happen is I want this negative 890.63 kilojoules to be canceled out here. Save this. So this is going to be a minus times a minus, which is going to give me a plus. Minus times a minus is plus 0.24298 kilojoules per Kelvin. And so I want this minus 890 to be canceled out by plus 890. So if I can make this term plus 890.63 kilojoules, then I can cancel out that favorable term. And so the easiest way to do that is just to set this to 0. So in other words, what we want to do is we want to transition from negative through 0 and then eventually to positive. We can make this favorable in the reverse direction. And so what temperature will make this term a plus 890? And so I'm going to solve for the temperature. So here I'm going to add an 890.63 to both sides and divide by this. And so I get the temperature is equal to 890.63 divided by 0.24298. This is kilojoules per Kelvin. This is kilojoules. So 890.63 divided by 0.24298. And I get a temperature of 3,665 Kelvin. Minus 273. So it gives us 3,392 degrees C. So if I could increase the temperature to about 3,400 degrees C, then the reverse reaction should be favored. Does that make sense? But this is not feasible, really. I mean, it's doable, not feasible in the practical. sense. Too high. So does that work for all reactions? All I need to do is increase the temperature. If I increase the temperature, the driving force goes down. Is that true or false? By increasing the temperature, the driving force for all reactions will go down. That's false, right? That's false because it depends. It depends on what's happening. It depends on what's happening with the enthalpy and the entropy. So if I'm looking at the driving force, delta G, I want a delta G, less than 0. A delta G less than 0 is the driving force, but that's going to depend on what delta H is and what delta S is in the temperature. So, for example, if delta H is negative, that's favorable. And if delta S is positive, that's favorable. And so this is what we call spontaneous at all temperatures. It doesn't matter what the temperature is. It's going to be spontaneous. And in fact, at higher temperatures, it's going to be even more spontaneous because delta S is favorable here. And so spontaneous at all temperatures. Increasing temperature will increase the driving force, not decrease the driving force in this case. Because this is a minus, and we're going to make this negative term even bigger. Let's say the enthalpy, it's endothermic, and the entropy goes down. So the energy goes up, and the entropy goes down. Then it doesn't matter what you do. It's always going to be a positive delta G. And what we say for this is it's going to be non-spontaneous at all temperatures. But you might say, well, what if I make a negative temperature? Then I can make it spontaneous. But can you have a negative absolute temperature? It doesn't exist. So there are no such thing as a negative temperature. So that's what I mean. Because the lower limit of temperature is 0. And so you can go up to 0. This is absolute temperature. Okay, that's not good, but what if it's exothermic, that's favorable, but the entropy goes down? This is what we had just now. And this is combustion of methane, which is spontaneous at low temperature. Well, what is low temperature? Low temperature is all temperatures below 3,400 degrees C. That's low temperature. Non-spontaneous at high temperature. What's high temperature? High temperature are temperatures above 3,400 degrees C, or 3,392 degrees C to be more precise. But that temperature is relative. Sometimes it's not this high, sometimes it's even higher. What if the energy goes up and the entropy goes up? Energy going up is not favorable, but entropy going up is favorable. And so this has a favorable entropy. To make entropy even more favorable, we do it at high temperature because increasing T increases the entropy term. The entropy term is favorable. So we say, on this case, this is spontaneous at high temperature, non-spontaneous at low temperature. And what that temperature is, what's high, what's low, again, depends on the system. So let's do an example of the last one here. An example of this last one would be H2O liquid goes to H2O gas. So this would be like boiling water. Is boiling water spontaneous at low temperature? No, but boiling water is spontaneous at high temperature. Well, let's take a look at what's happening with delta H. If we look at delta H, is delta H positive or negative? In order to boil water, do you have to add energy or do you have to remove energy? You have to add energy, so this is endothermic. What's happening with the entropy? Is the entropy increasing or is the entropy decreasing? Well, we're going from a liquid. Yeah. Liquid is more constrained and therefore it has to be more ordered. You know, the more constraints you have, the more ordered it is. Compared to gases. Gases are less constrained, and the fewer the constraints, the more disorder we can have. And so everything has to, actually for the liquid, everything has to touch. They're being held together. So delta S is actually favorable, is greater than 0. And so this is unfavorable. This is favorable. All right, and so let's take a look at how we can make this whole thing unfavorable. So this would be a scenario where it's going to be favorable at high temperature. High temperature is going to favor the entropy. And so delta G, okay, now we're going to be restricted. This is going to be delta G naught, and we're going to do this at temperature T. But our data is at 298. And so what we're going to do is we're going to use delta H naught at 298 minus T delta S naught at 298. And since that's not entirely accurate, I'm just going to put a little approximately equal to or tilde there. So let's go ahead and get the data. I'm going to get my delta H of formations. For H2O liquid, I had that earlier, so let's grab that from up here. Actually, I don't have that. We'll grab that off the appendix D. H2O liquid, delta H of formation minus 285.8. Minus 285.8. H2O gas, minus 241.8. Minus 241.8. And what are the units for delta H? Kilojoules per mole. All right, let's look at the absolute entropies. The absolute entropy for H2O liquid, 69.91. The absolute entropy for H2O gas, should be higher, 188.8. The units for entropy, what?
Per mole Kelvin?
Yeah, joules per mole Kelvin. All right, so let's go ahead and calculate our delta H. It's just this minus this, and that's going to be 44.0 kilojoules. We're dealing with 1 mole. Okay, minus T, and then let's go ahead and calculate delta S. Delta S is going to be about 100. It's 188.8 minus 69.91. 118.89. So it's 118.89 joules per Kelvin. Okay, this I'm going to convert into kilojoules. 1 kilojoule is equivalent to 1,000 joules. Or just move the decimal. It's 0.1188. 2.89. So let's do a temperature equal to 298 Kelvin. If the temperature is equal to 298 Kelvin, then this is equal to, go ahead, so 118.89 divided by 1,000 times 298 equals minus 44. And it comes out to a delta G at 298 of plus 8.5707 kilojoules. So what this tells me is it's non-spontaneous here in the forward direction. Let's recover this. And it's spontaneous in the reverse direction. Come on. Reverse direction spontaneous. So at 298 Kelvin, steam should condense into liquid water. That's what we expect. I guess it's positive. Positive delta G's, non-spontaneous. The next calculation is at what temperature will this become spontaneous? Can you calculate it? And so what I need to do is, this is frozen again, but what I need to do is I have plus 44. So I got to make this term minus 44. If I can make this term minus 44, then that's going to cancel that out, take me to 0. And so what I'll need is I'll need this to go negative. So I need this one to be bigger than minus 44. If this one's bigger than minus 44, then this whole thing's going to come out negative. And so I want that temperature at which it transitions. That temperature at which it transitions is I'll set this equal to 0 and then solve for T and see what that temperature comes out to. Well, that temperature comes out to about 97 degrees Celsius, which is off a little bit because at what temperature should water boil? At 100. And there are two reasons it's off. One reason it's off is because we're using delta H at 298 and delta S at 298, so it's off. We should be using delta H and delta S at those temperatures. The second reason it's wrong is because 100 degrees C is the boiling point at a pressure of 1 atmosphere. This data is not at 1 atmosphere, this data is at 1 bar, and there's 1.01325 bar in an atmosphere. Water doesn't boil at 100 degrees C under 1 bar. So we'll calculate at what temperature water boils at 1 bar. Okay, I'm out of time, so I'll stop here, but that's what we're going to do next time.
Let me know what I hand to you. Here's my.
Is this you're handing in late, or did you have this?
I had it tested, but I hadn't turned it in with you.
How come you didn't turn it in on the day of the test? I mean, was it done before the test, or did you do it after?
I had a couple things I didn't finish, that's why I
okay.
didn't have it ready for you, but
Okay.
I understand. I turned it in.
Yeah, it's okay. I just need to know. Officially, it's due before the
Okay.
test,
Thank you.
but I'll take it.
Appreciate it.
Sure.